Technology Directorate at the Department of Homeland Security, and now will make a presentation on their recent study.
Thank you, Mr. Vice President. Thank you, Mr. President, for this opportunity to do this today. Good afternoon, everybody. My name is Bill Bryan, and I lead the Science and Technology Directorate at the U.S. Department of Homeland Security. Over the last several months, we've intensified the department's R&D efforts to identify and deliver information that informs our response to COVID-19. S&T is working to identify, develop, deploy the tools and information to support our response to this crisis. As part of our efforts, we're leveraging the unique capabilities of S&T's National Biodefense Analysis and Countermeasure Center to study the biology of the COVID-19 virus. This center is a high biocontainment laboratory located in Frederick, Maryland. It was established in the early 2000s in response to the Amerithrax attacks, and where we study, characterize, analyze, and develop countermeasures for biological threats to the homeland. We work closely with the CDC, FDA, HHS, and also our Department of Defense colleagues and many others. Yesterday, I shared the emerging results of our work that we're doing now with the Coronavirus Task Force. And today, I would like to share certain trends that we believe are important. If I may have the first slide, please. And while that's coming up, our most striking observation to date is the powerful effect that solar light appears to have on killing the virus, both surfaces and in the air. We've seen a similar effect with both temperature and humidity as well, where increasing the temperature and humidity, or both, is generally less favorable to the virus. So let me illustrate with this first slide. If you look to the right, you'll see that term half-life with a bunch of time stamps on there. First, let me tell you what a half-life is. We don't measure the virus as far as how long will it live on a surface. We have to measure the decay of the virus in terms of its half-life, because we don't know certain elements. We don't know how much a person expectorates when he spits, right? When he sneezes, whatever the case may be. We don't know how much virus is in there. So that has a bearing on how long the virus is going to be alive and active. So we measure it in half-life, because half-life doesn't change. So if you look at an 18-hour half-life, what you're basically saying is that every 18 hours, the life of the virus is cut in half. So if you start with 1,000 particles of the virus, in 18 hours you're down to 500, in 18 hours after that you're down to 250, and so on and so forth. That's important as I explain the rest of the chart. If you look at the first three lines, when you see the word surface, we're talking about non-porous surfaces, door handles, stainless steel. And if you look at as the temperature increases and as the humidity increases, with no sun involved, you can see how drastically the half-life goes down on that virus. So the virus is dying at a much more rapid pace just from exposure to higher temperatures and just from exposure to humidity. If you look at the fourth line, you inject the sunlight into that, you inject UV rays into that. The same effects on line 2 at 70 to 75 degrees with 80% humidity on the surface, and look at line 4, but now you inject the sun, the half-life goes from 6 hours to 2 minutes. That's how much of an impact UV rays has on the virus. The last two lines are aerosols. What does it do in the air? We have a very unique capability. I was discussing this with the president prior to coming out. He wanted me to convey it to you on how we do this. I believe we're the only lab in the country that has this capability. But if you can imagine a Home Depot bucket, a 5-gallon Home Depot bucket, we're able to take a particle, and this was developed and designed by our folks at the NBAC. We're able to take a particle of the virus and suspend it in the air inside of this drum and hit it with various temperatures, various humidity levels, multiple different kinds of environmental conditions to include sunlight. And we're able to measure the decay of that virus while it's suspended in the air. This is how we do our aerosol testing. We work with Johns Hopkins Applied Physics Lab, and we actually developed a larger drum to do actually more testing, and it's 4 times the size of that. So this is the capability that we bring to this effort. So in summary, within the conditions we've tested to date, the virus in droplets of saliva survives best in indoors and dry conditions. The virus does not survive as well in droplets of saliva, and that's important because a lot of testing being done is not necessarily being done, number 1, with the COVID-19 virus, and number 2, in saliva or respiratory fluids. And thirdly, the virus dies the quickest in the presence of direct sunlight under these conditions. And when you look at that chart, look at the aerosol as you breathe it. You put it in a room, 70 to 75 degrees, 20% humidity, low humidity. The half-life is about an hour. But you get outside and it cuts down to a minute and a half. Very significant difference when it gets hit with UV rays. Mr. President, While there are many unknown links in the COVID-19 transmission chain, we believe these trends can support practical decision-making to lower the risks associated with the virus. If I could have my next slide, and while that comes up, you'll see a number of some practical applications. For example, increasing the temperature and humidity of potentially contaminated indoor spaces appears to reduce the stability of the virus. And extra care may be warranted for dry environments that do not have exposure to solar light. We're also testing disinfectants, readily available. We've tested bleach. We've tested isopropyl alcohol on the virus, specifically in saliva or in respiratory fluids. And I can tell you that bleach will kill the virus in 5 minutes. Isopropyl alcohol will kill the virus in 30 seconds, and that's with no manipulation, no rubbing, just spraying it on and leaving it go. You rub it and it goes away even faster. We're also looking at other disinfectants, specifically looking at the COVID-19 virus in saliva. This is not the end of our work as we continue to characterize this virus and integrate our findings into practical applications to mitigate exposure and transmission. I would like to thank the President, thank the Vice President for their ongoing support and leadership to the Department and for their work in addressing this pandemic. I would also like to thank the scientists, not only in S&T and the NBAC, but to the larger scientific and R&D community. Thank you very much.
Bryan. Mr. Bryan.
Thank you very much. So I'm going to ask Bill a question that probably some of you are thinking of if you're totally into that world, which I find to be very interesting. So supposing we hit the body with a tremendous, whether it's ultraviolet or just very powerful light, and I think you said that hasn't been checked, but you're going to test it. And then I said, supposing you brought the light inside the body, which you can do either through the skin or in some other way. And I think you said you're going to test that too. Sounds interesting. Right, and then I see the disinfectant where it knocks it out in a minute, 1 minute. And is there a way we can do something like that by injection inside or almost a cleaning? Because you see it gets on the lungs and it does a tremendous number in the lungs. So it'd be interesting to check that. So that you're going to have to use medical doctors with. But it sounds interesting to me. So we'll see. But the whole concept of the light, the way it kills it in 1 minute, that's pretty powerful. Steve, please.
You say that the country will be in a better place by early summer. Does that mean you're going to need to extend the social distancing guidelines until then?
Well, we may, and we may go beyond that. We're going to have to see where it is. And I think people are going to know. You're going to know. I'm going to know. I think people are going to know just out of common sense. At some point, we won't have to do that. But until we feel it's safe, we're going to be extending.
You have 23 cases where 23 states where new cases are on decline. What does that mean about when the country can be safely reopened to a more normal point?
Yeah, but it means we're going to watch those cases very carefully. I think we've all gotten very good at it. We've gotten good at tracing. We see where the cases are, where they're going, and we're going to be watching it, and it's called containment. At a certain point, we're going to be able to contain. And, you know, when you see this, a lot of people have been talking about summer. Maybe this is one of the reasons. I once mentioned that maybe it does go away with heat and light, and people didn't like that statement very much. The fake news didn't like it at all, and I just threw it out as a suggestion. But it seems like that's the case, because when it's on a surface that would last for a long time, when that surface is outside, it goes away very quickly. It dies very quickly with the sun. Yeah, go ahead.
You said yesterday that you're going to look into Senator McConnell's suggestion for allowing states to declare bankruptcy versus the aid.
Yeah, we'll look into it, and I have been looking into it. I've been talking to a lot of the different senators, but I don't want to talk about it now. That was a very interesting presentation. Go ahead, Jim.
Well, I wanted to talk about McConnell's suggestion that aid to the states amounts to
I just told you I'm not talking about it now. I'll talk about it later. Okay. I'd like to talk about something that right now is of more interest to people.
Could I ask Mr. Bryan a question?
Yeah, sure.
Thank you. When you started your presentation, you described this as an emerging result. Does this mean your study is conclusive? Is there more work to do?
We're continuing with that. For example, on the aerosol side, you notice the figures were 20% humidity. We're looking at higher humidity levels. We would expect that would even have a greater impact on the virus. We're looking at other types of disinfectants. And so we're as a scientific community, we're continuing to study the virus to understand its characteristics.
Mr. Bryan, can you explain why some hot spots we've seen in the U.S. are hot and humid, like New Orleans, for example?
Let me explain. If you look at the coronavirus as a chain with many links, what we've done through our study is we've identified some of the weak links in that chain that the transmission of the virus depends upon. We identified that heat and humidity is a weakness in that chain. We've identified that sunlight, solar light, UV rays is a weakness in that chain. That doesn't take away the other activities, the guidance from the White House, the guidance from the CDC and others on the actions and steps that people need to take to protect themselves. This is just another tool in our tool belt, right? Another weapon in the fight that we can add to it. And in the summer, we know that summer-like conditions are going to create an environment where the transmission can be decreased, and that's an opportunity for us to get ahead.
But the president mentioned the idea of cleaners, like the bleach and isopropyl alcohol you mentioned. There's no scenario that could be injected into a person, is there? I mean,
No, I'm here to talk about the findings that we had in the study. We don't do that within that lab, our lab. So.
So how do you?
Are we simplifying through injection? We're talking about almost a cleaning, sterilization of an area.
Right.
Maybe it works, maybe it doesn't work, but it certainly has a big effect if it's on a stationary object.
Okay.
So how do
Are
you?
we simplifying too much by saying that it'd be better with the warmer weather and the sun coming out more and more, that people would be outside than staying inside their home, confined to the four walls of their house?
It would be irresponsible for us to say that we feel that the summer is just going to totally kill the virus and that if it's a free-for-all and that people ignore those guides. That is not the case. We have an opportunity, though, to get ahead with what we know now and factor that into the decision-makings for what opens and what doesn't.
But
So-
are you saying on surfaces, the heat, the hot summer, and whatever other conditions, humidity and lack of humidity, that would have an impact? So that on surfaces where it can be picked up, it will die fairly quickly in the summer, whereas in the winter it wouldn't die so quickly?
Yes, Mr. President. When it's exposed to UV rays, take a playground equipment, for example. The UV rays hitting a piece of playground equipment will kill the virus when it hits on the playground equipment. But underneath, where the sun does not get, if someone touched that and had it on their hands, it could still be there, right? It has to be in direct light of the UV rays.
With the sun, if it's on somebody's hands, right, and they haven't touched their face and all of the things.
And
that
it's
we've
exposed
all
to
been-
the sun.
I know, but if they're outside, right, and their hands are exposed to the sun, will that kill it as though it were on a piece of metal or something else?
I don't want to say it will at the same rate because it's a non-porous surface, but what we do know is that we looked at the worst-case scenario, and the virus lives longer on non-porous surfaces. So porous surfaces, it doesn't live quite as long. So in theory, what you said is correct.
This is sort of semi-non-porous, right? This, right?
Yes, Mr. President.
Mr. Ryan, how should governors, Mr. Ryan, to do this?